I will be presenting on a topic which I named From Token to Geometry, Understanding Numerical Representation in Large Language Models. So this presentation is not just about like a single paper. I have gone through a bunch of papers and how we should represent numbers, which are like very common in text data, uh, differently from how we represent the usual text tokens in large language model and how that can affect how the language model perform. So to start, the first motivation for this entire area of research is that we have observed in like past few years that LLM now reason brilliantly on tasks, for example, say a document analysis, or if you ask it to like even prove a theorem, it will reason brilliantly, yet stumbles upon basic number operation like say 8-digit addition or 8-digit multiplication, and that is like kind of funny because it is doing like a very complex task easily and very easy task like it try to do some complex calculation over it. And the reason is that, as we can say, LLM can solve like multi-step logic puzzles, write code, and summarize 100-page documents, but struggles with, say, there is this very famous example when, so it's from like 2 years ago. So I hope they have like do have done something to address this thing. But people ask ChatGPT model which of the number in like zero point 0.9 and 0.11 is bigger, and which of the number in 9.11 or versus 9.99 is bigger, and surprisingly, GPT gave wrong answer in both these cases. It was not able to do digit counting and large arithmetic tasks, though. Like from that point onwards, there have been some like way around of doing these tasks. Like you can integrate a tool, you can write a program to basically execute these tasks and actually get an answer. But the actual core limitation is still there. That model on itself cannot basically reason out or cannot perform operations on these numeric tasks, which are relatively easy compared to what other task model can do, right? And why? So one can ask this question very easily: why number matters at all? Because they are everywhere. Even if you are like, if you want to summarize a financial document, for example, if I want to like just so if I want to audit a document, or if I want to summarize a healthcare document, then or any field and domain of science, say you want to do some kind of measurement, you want your LLM to draw you a map or something like that, you need numbers for all these tasks, and it is necessary for model to at least understand what numbers are and kind of preserve their inherent behavior, their continuity, their periodicity, and not just like tackle them as some random tokens which are there in the text, like it treats other word tokens, because uh, text naturally is like discrete in nature, whereas number inherently are continuous and they have their particular behavioral properties which should be preserved when you are basically, when language models are basically understanding those numbers. And it leads to the whole topic of how number embedding should be in language models. So first of all, I will like to point out like four big problems which happens when try to do numerical task. First is the tokenization mismatch. So because most of the language model use the subwords or character-wise tokenization mechanism, they often tokenize numbers as arbitrary substring. So there is no concept of quantity in like encoding, which is like encoded in the token itself. For example, when I say one, every one of us have some kind of quantification or a quantity related to this particular number in our mind. When I say 1,000, instantly it goes from, oh yeah, it's a big number. There's a quantity or a like sense of quantity associated with each number. And when you tokenize, for example, say if I'm tokenizing, say 1, 2, 3, 4, like one, so it's in our mathematical world, it's like 1,234. It's a number, it's a quantity. But like when LLM tries to like tokenize it, it might tokenize into say 1, 23, and 4, and then it loses its entire meaning. Uh, Again, so second point leads us to there that tokens do not capture the precise value that separates numeric from textual data. So the way you separate numbers from text, there is no like distinction between that. The So this is on tokenization, right? Then there is another thing that, okay, even after tokenization, say I have a number vocabulary. When I try to learn the embedding, now we all know that the way that word embedding is learned is based on their frequency in text corpora, on which the model is being trained. Like, what is the so the for example, if you say something like water, you can relate it to something like, say, waterfall or something like water is flowing. So, I mean, the word embedding are based on the frequency and the associativity of the other words uh, where they occur in the text. And if we train the language models in a similar way of number, the embedding, so basically the embedding geometry will reflect the corpus frequency. For example, if one occurs quite a few times, model will assign a very um, kind of a easy embedding, or an embedding which is different from other numbers to one because it sees it a lot of times, and it does not encode the numeric magnitude. So common numbers are represented better than the rare numbers, but this kind of frequency bias should not be there, because even if some number occur more than other number, every number has its own identity in the number on the number line. Then the last point is the multi-token aggregation burden. So as I say, now you cannot encode, say, a 10-digit number as a single token in the model, because there is no token corresponding to that particular number in your vocabulary. And because you have to like limit your vocabulary somewhere, you then divide those numbers, those bigger numbers, into substring. You can use like subword tokenization mechanism, where say if I say k equals to 3, I will divide the number into 3, 3, 3, and 1 chunks. If I do a digit-wise tokenization, I'll divide the 10-digit number into 10 different tokens. And then it is on the model to basically learn to then aggregate the number embedding of all those numbers and then make sense of it, because the tokenization of say 1, 2, 3, 4, if I tokenize them digit wise, what I'll get in my input embedding is the embedding of 1, embedding of 2, embedding of 3, embedding of 4. Now, based on their position in this number, they can form number like 1234 or 2134, and those two are like quite different numbers. So it's on model to basically then figure out a mechanism how to combine these based on their relative position in the number, like in digit itself, and then tries to make a sense of that number and then perform operation on it. So like we are adding some extra burden on the model at the start as well. So these are like few limitations which have been there like for a long time now in language models, and now the researchers are like trying to come up with strategies in which way you can like more naturally encode numbers, so that model now just have to learn how to manipulate these like vectors in the embedding space to come up with new answer. For example, say if I want to do addition, if I have vector embedding, or like so embeddings are vector like in n-dimensional space, where n dimensional is your d model. So in that case, when say if I have a number embedding of 1 and 2, which are like say totally orthogonal in nature, they don't have any similarity, any relationship, how would I expect a model then to like calculate 1 plus 2 equals to 3? It would be very difficult for the model. But if I have some number embeddings which naturally encodes the magnitude and the direction, so that when I try to like do some kind of trigonometric or geometric operation on these vectors, I rotate them, I translate them, I add them together, I manipulate them, and then it results in the actual embedding vector of number 3. I just have to decode that. So it is very easy for the model to basically then learn only those kind of geometrical manipulation in the vector space to perform different kind of arithmetic operation over these learned numeric vectors. So it would make a lot more sense to model to basically then interpolate and extrapolate really well on numeric tasks rather than try to do pattern matching and come up with some kind of heuristics to basically then solve these problems. Any question till this point?
No.
Okay, so let's move. Then, okay, so this is example of how numbers are tokenized. So for example, a small number can be tokenized as a single token, which is why we see the so for example, if you test language models on numeric benchmark, like mathematical reasoning benchmark, like say GSM-8K or say Aqua or say multi-arithmetics, you would find them to be like doing very well because most of the numbers which are involved in those calculations are a single digit or two-digit number, and based on your subword tokenization, you probably will tokenize these numbers as single token, thereby preserving at least some part of their natural behavior. So here the patient received 5 milligram of some medicine, so ibuprofen here. It's like you tokenize five as one token. So at least quantity is intact. You still don't know about its relation with other numbers in proximity of this number. For example, how it is related to number six or how it is related to number four. But at least we can say that the quantities of this number is intact here. Then a larger number. Now you fragment it across tokens 21, 433, and 226. No, this is actually a single number, but when you tokenize it, now model must aggregate this fragment and aggregate in a way that 226 is towards the unit place, tens place, and hundred place. Then there is 433 and the 21, though it's the absolute magnitude of 21 is the lowest in this whole number string. It is the most significant digits here. These two are like most significant digit in this entire number. So model this falls on model now to basically learn to aggregate these kind of numbers and then make sense of it. And then third is basically when it is mixed in sentence uh, or it's float. So I mean, for example, rate rose from 3 percentage to 11.75 percentage. Now, percentage in itself is an operation of what the rate initially was, and then 11.75. Now, this decimal point is a token which is similar to a full stop token in text. So you can't have different embedding for these tokens. Now the model has to understand, okay, because this is between two number embeddings, it's not a full stop. It's not like 11, then full stop, then 75% with respect to something else. It's actually a decimal point number. So I hope like from this, it is clear that using the tokenization mechanism or schemes which we usually use for words is not quite like right for numbers. Here I present a graph or a result graph from a paper which published last year in ICRA 2025. The paper name is Number Cookbook if anybody wants to like refer that paper. What they did was they basically tested different mathematical operations with varying range of say numbers like say small. So here's this S, M, L in Excel. So small numbers are basically number with 1 to 4 digit, then you have 4 to 8 digit as medium numbers, 8 to 12 digit as large number, and more than 12 digit number as Excel. And they tested it across like four different format of numbers. So we have integers, we have float, we have scientific notation, and we have fraction. And then you see there is addition task, there is like max task. So you try to extract like a maximum from a list of integer, you try to extract a maximum from a list of fractions. Um, you have like say a true division, floor division, where you just give the remainder, sorry, the quotient only, not the remainder. And so like these tasks, and then multiplication. And they tested that not on the open source model, but on the very good industry level proprietary model. So this paper is because it's from last year when they were testing that at like say December 2024. These were the state of the art models. So GPT-4o, GPT-4o mini, Qwen 2 72b, Qwen so say Llama models, Llama 3.1 family, Llama 3.170b. So like quite a big models are there as well. And as we can see, so on a small digit integer addition, the accuracy is pretty good. But as we move from small digit addition to large digit addition, it drastically falls down. And even model like GPT-4o and GPT-4o mini are performing around say 40%. And this is even worse on float numbers, and on fraction it does not even exist. So this kind of paints a picture that what we are testing in benchmarking and saying that okay, the models have a good mathematical reasoning ability, yeah, they can reason what operation to perform, but they cannot perform that operation precisely. So that's a gap. For example, model may know that okay, I want to add these two numbers, but it cannot add those numbers correctly more often than not, because the the number itself does not make sense to model. It has to kind of somehow do some kind of learn some kind of heuristic to then add those two number, or to perform that operation, or to multiply them, or to do any other arithmetic operation on that number. So it kind of points out a bigger gap there, that if we have some kind of embedding where model learns okay to like manipulate the geometry of these vectors to get a precise answer, then a model might be able to basically perform really well on scientific data modeling. And if we are going to like adapt LLM into the STEM domains, for example, we are now using them to control systems and like trying to do research using those models. They must understand these numeric or symbolic data precisely, or and also encode its natural behavior the way how human understand that, so to actually make any good progress towards the final like cognitive reasoning abilities which we are trying to basically replicate using language models. So this was like an overview of where the problem is. If anybody has any question till this point, you can ask.
No, go ahead.
Okay. So then these are some baselines. Why I'm saying these as baselines is because they are used in research paper, which I'll discuss later, to test their embedding mechanism. But still, these are not used as baseline in the language model. Language models still use subword tokenization, digit tokenization, especially the open source models. The proprietary models, say now Gemini, like Gemini 3 or GPT, the newest GPT model, they perform really well on mathematical tasks as well. But no one knows which kind of embedding they use. So, I mean, we can't say anything about that. But open source model, they still use subword tokenization. But these are very basic tokenization mechanism which were used in natural language tasks before LLM came into picture. So that's why these are used as baselines in the papers which I'll discuss later. So first is called P10, which is power of 10 encoding. So you represent number as sum of digits and their decimal place component. So it's like you add a decimal place, and it's basically a necessary condition because this is the least kind of costly, or like you don't have to learn things for this. You just have to encode the 10 power as a positional in embedding with the number, and it kind of dramatically increases the model's ability to basically do mathematical tasks, because at least now model know in which order to combine embedding of these number. So as I said, now 1 2 3 4, these four number can make lot of different number. Like there are a lot of combination of what numbers you can make using these four digits. Now if I tokenize them digit wise and give them to model, at least I should tell model in which order model has to aggregate these digits. So this is like the simplest way of doing it. It's just you just add like 10 to the powers. So this is like ones place, tens place, this is hundreds place, this is thousand place. Combine them in order and just hope that model learns that. So yeah, that was the easiest one of that. That's called P10. The problem with P10 is now what if you're dealing with a 20-digit number? You might be encoding say 20 tokens for one digit, and it will increase context length by a lot, and you don't want that often. So they come up with like p100, which is power of 100 encoding. So now you encode two digit together and in power of 100. So again, 100 to the power 0 is the tens place, 34 goes there, 100 to the power 1 is the hundreds place directly. So instead of moving in increment of 10, multiple of 10, you move in multiple of 100, thereby kind of like reducing your tokenization length by half. So that's a way around that. Another was B1999. This is the bucket 199 encoding, which numbers, which like represent number by assigning them to one of approximately 2000 magnitude buckets. So they have divided number from 0 to 9, then 11 to 20, say 0 to 10, 11 to 20, and like those buckets, and then you like encode numbers using that bucket K. Now, this is not a very natural kind of number embedding. It's just like this is useful when you try to do some kind of modular operation. So, for example, if I want to do the like modulus addition or modular addition, I might want to use this because in my mod space, say if I'm doing mod 10, every number falls into equivalence class from 0 to 9, right? So this would become more useful there, and not for continuous tasks like natural, like the simple addition, multiplication, division, or something like that, or counting, or taking maximum tasks like that. Then now these are for integers specifically. You can't encode like say float using this. I mean, you can, but there would be a decimal token in between. Then you have to figure out a way to basically encode that again. So FP15 is floating point 15 encoding, which represent number like a float point, as we do in say electronic circuits or like any other number domain. So what you do is you have like three values: a sign, mantissa, and an exponent. So that is how you encode like these numbers. Now, again, these are like very basic strategies, and they have a lot of run. For example, FP15. Now, you can encode because sign would be plus or minus, so you can basically specify two vocabulary spaces for plus and minus embedding. But what about 1.234 and 10 to the power 3? Because they may vary for all the numbers. You can't encode all of them. You can't assign a vocabulary, or you can't design a vocabulary where you can basically map all of these numbers like uniquely to a particular number embedding. So in the end, you would divide them like digit wise, or you would do some kind of server tokenization. And then, so for 10 to the power 3 can be encoded as a positional embedding because it's based on the number of digits in the number, right? But the main magnitude, which is 1.234, or any other magnitude which comes from the number, you cannot like uniquely map it to a particular embedding in vocabulary, because that would be out of vocabulary after some time. So yeah, I mean, but these are the baselines which are used by the later model, because at least like instead of just using plain subword tokenization and some random like frequency based embedding where you just like try to learn embeddings based on how frequently the number occurred in the corpora, these are a bit more structured in nature. Now, okay, so I think I should switch to my iPad. Wait a second. Mm. Okay, so now I'll start with the first method, which is uh, termed as XWell, which is a continuous number encoding for large language models. Now, one thing which we have observed is that number continuity matters a lot, right? So what they do is, and because you cannot map each number uniquely in a vocabulary space, so we cannot design it like, oh, we tokenize every number as single token and then get its vocabulary from the vocabulary space, because that might not be feasible after all. So what they do is they try to represent real number using a single token. So first of all, they don't want to tokenize it because, as we have seen, tokenizing number into multiple fragments kind of like compromise their quantity and quality. So but what they do is, the core idea is it represent a real number by scaling a dedicated embedding vector by the numerical value. So what they are actually saying is that, for example, if I draw a two-dimensional embedding space and I assign a certain vector, say this one here. Now, this vector, say, is u, right? Now, the vector u here, we can basically get a unit vector corresponding to this, which would be your, and this is a particular direction in the embedding space. Now, because this is a 2D embedding space, this is just a simple vector we can visualize. If it's say an ND space, it's still a vector which points in a particular direction. So it would represent a particular axis in the embedding space, right? What, so not the axis like the which are orthogonal to each other, but particular direction, right? A particular dimension in the embedding space. And that dimension is used to encode all the numbers. How? You have this unit vector, so now there is no sense of magnitude associated with this unit vector here. And I have a magnitude, say I want to encode, say, again, 1, 2, 3, 4. How XWell encoded this number is, you basically encode it as x to this magnitude in this particular direction. So now embedding of 1, 2, 3, 4 is basically just a, a, a unit vector multiplied by that magnitude. So in that dimension, that magnitude vector. So magnitude of vector basically represent magnitude of number here. So it basically kind of collapse all the numbers to a single vocabulary, because in your embedding matrix, you just have to learn embedding of this base vector, and then you just multiply or scale that base vector with a magnitude of the value, and then you get the embedding of the particular number. So you don't have to have like a 101 mapping of all the numbers to a particular, say, embedding. You just have to have a mapping of this u vector, which model will learn basically over the course of your training, and then you just scale that vector by a value of the number to basically arrive at a particular number embedding. So here, uh, let me start. Just, okay. So I'll do some derivations now. So I hope you guys will understand it like clearly. Okay, so for example, normally a language model with a D model dimension encodes numbers as random vector. For example, if I have two numbers, say 2 and 3. Now they might be encoded as something like you have some random values, right? Until, say, it's endim vector, and again this would be something again an n-dimensional vector. Now, where these both vectors are in high dimensional space, but they do not represent any inherent relation between these two numbers. Now, concept of xval is as instead of storing number as an unrelated tokens, x will encode numeric magnitude along one learned dimension in the embedding space. Now, what do I mean by that one learned dimension in the embedding space? So basically, it's a unit vector. So this direction would correspond to a unit vector. And this is basically in the T model domain. So we have like, so it's the in again in the RD space or RD model space. And then you have the numerical aspect of the number. So the magnitude of number, say, is M. And then basically your number embedding under this XWell is basically, I would say XWell X or XWell M is basically M multiplied by this unit vector. So this is basically the core general idea of the XWell. Now, in general, you won't just encode this, but actually you would encode a base vector with it, which will basically then have information regarding its position relative to the text and everything. So all the other information can be, so they kind of like represent this base vector is all the other dimensions on which you will represent this number, because you won't just represent this number on this one dimension, right? You would represent other informations as well with the number. And then you have this so this particular dimension or direction in your embedding space is for kind of encoding the magnitude of the number. And rest of it, you can just, encode using any other base vector in the embedding direction. And the ideal scenario is that your base vector is kind of orthogonal to your learned embedding direction. So I mean, I can just remove M here. It is like orthogonal to this particular thing, right? So why orthogonal? Because there is no similarity between them. So you can basically separate the dimension on which you have encoded the number or the magnitude of the number, and any other dimension encoding information related to anything other than the magnitude of this number. So that is first like concept which base val which like your x val introduced there. So now, and this like this numeric access also should be ideally learned in the way that when you project it, so when you project back, so the projection of your embedding of this number and your direction vector will basically should basically give you the number back. So when you project this embedding of the number learned, so again, if your orthogonal, if the base vector and the magnitude vector, which or the number axis on which you have encoded the magnitude are orthogonal or like uh, very have very low similarity between them, so like approximately orthogonal, when you will project this entire embedding on the direction vector, you will basically recover the number's magnitude only with some noise, but not a lot of noise. If they are not orthogonal, you might not be able to basically then kind of like recover the number back from the embedding, like the numbers embedding direction, because then both the vector are either in the same direction or like very similar to each other. And when you project them, they might end up their projection might end up very similar to each other. So you basically cannot kind of uh, recover the actual number. But if they're orthogonal, the projection of your base vector would be actually zero. So you would recover the number, right? Any question till this point?
Yeah, hi. Yeah, just a quick question.
Yeah.
As you mentioned, for like right now, n-dimensional vectors are used for representing the number, right? In like encoding. But in this scenario, we have the base vector and then we have this orthogonal thing, right?
I mean, so
So,
base vector is a term which is used for if you have any other vectors which
mm-hmm,
encode any different information about the
mm-hmm,
number. For example, what the format of number is,
mm-hmm,
if it was used in, say, some kind of measurement task or something like that. But the idea is if all those base vectors or base vector in combined uh, are like orthogonal with this particular learned direction vector,
mm-hmm,
then when you project this on, so you when you project the embedding of this number onto the direction vector in particular, you would basically recover the number only, because when you project,
mm-hmm,
projection is like taking a dot product, right?
mm-hmm. Yeah,
And
got it.
if the
Yeah.
vectors are orthogonal to this particular vector in itself or this particular dimension, then when you project the embedding of the number on this dimension, only the magnitude which was encoded in this direction particularly would
Mm-hmm,
be the main part of your projection, and rest of the vector, if they're ideally, they should be like 100% orthogonal, so every
mm-hmm,
vector is on 90-degree angle. It
mm-hmm.
might not be the case in the model because that is not how model behaves. But if you have them, like if they're sufficiently orthogonal, they might
Mm-hmm.
just they might just like introduce a bit of a noise, but the major part of your recovered projection would correspond to the number itself.
Okay. So is the base vector is same like which has been used so far in encoding that random and dimensional or because I
Yeah, I
feel
mean,
like
base vector is model
it's the
can
same.
learn. So for
Mm-hmm.
example, what I mean by an n-dimensional is that a particular number embedding
Mm-hmm.
in this n-dimensional space would be can be a random vector. For
Mm-hmm.
example, one can be so if I draw like a 3D space, because 2D
Mm-hmm.
space like is quite trivial for this thing.
Yeah.
So for example, if I draw a 3D space like the entire 3D space, all the coordinates of the 3D space. Now, one random vector could be this,
Mm-hmm.
right? And another random vector could be, say, this.
Mm-hmm.
Now, if this is my 1 and this is my 2, there is no inherent, and say, for example, my 3 goes here,
Mm-hmm.
right? There is no inherent relation between these two, like these three vectors at
Mm-hmm.
all,
Mm-hmm.
right? What they are saying is in this entire space, sorry, what we would do is we assign a particular direction or a dimension, say this particular direction, for encoding magnitude of all the numbers,
Mm-hmm.
right? And then I can encode anything other than this. So for example, not even if like this is not the first dimension you would say, because here you just have like three dimensions, right? So I would say corresponding to x axis
Mm-hmm.
is my dimension of mapping magnitude of this, right?
Mm-hmm.
And if I, so because this is a embedding space where your support vectors are basically orthogonal by nature, it's a 3D space, right?
Mm-hmm.
So every axis vector or every dimension is basically 90-degree to the other dimensions, right?
Mm-hmm.
So if I have a random vector now, again, this is a random vector again, but
It's the same.
what it
Yeah.
is, so but and it can encode anything on my y and z
Mm-hmm.
axis.
Mm-hmm.
But what I'm saying is on the x-axis, it would encode the magnitude of that number.
Mm-hmm.
So when I project this back on my x-axis,
Mm-hmm.
I would recover my number back. And because these are the orthogonal vectors,
Mm-hmm.
when I project this on x-axis,
Mm-hmm.
whatever I encoded in y and z
Mm-hmm.
dimension basically vanishes away.
Mm-hmm. And we'll
And
get the number. Yeah.
in that way, we can get the number. Now, this
Mm-hmm.
is a very ideal space because by nature, a 3D space like this have all the axes or dimensions which are orthogonal to each other.
Mm-hmm.
When we say an n-dimensional space, we don't know because those dimensions are also learned. I mean,
Yeah. Mm-hmm.
there are research showing that, okay, you, for example, there is a famous famous like example which you also
Mm-hmm.
may have gone through, is that
Yeah.
a king and queen on authority dimensions are very you take cosine similarity, they're very close, and on the
Mm-hmm.
gender dimension, they are like they should be like orthogonal, or there should be no similarity, right? Because it's
Mm-hmm.
opposite, right? Now
Yeah.
that is a kind of assumption which people had made when they were trying to
Mm-hmm.
like do interpretability work. In
Mm-hmm.
reality, the dimensions are not encoded as like, okay, this is dimension for the say gender, this is dimension for say authority, this is dimension
Mm-hmm.
for say if it's a human or
Yeah.
not.
Mm-hmm.
The model learns them on the fly, and they might not be orthogonal, right?
Mm-hmm.
In that n-dimensional space.
Yeah.
The ideal condition is that all these dimensions are orthogonal, and
Mm-hmm.
then you encode and you learn to basically, and then basically what I mean by learn is to basically pick a dimension
Mm-hmm.
among all these n dimensions to encode your
Mm-hmm.
number over that dimension.
Mm-hmm.
And then whatever the rest of the part in your vector, basically it can mean, so it can be 0 0 0, so it does not encode anything. It
Mm-hmm.
can encode some other things related to other contexts of the number.
Mm-hmm.
But when you will basically project them on this particular learned dimension, you will
Mm-hmm.
recover the number. So along
Mm-hmm.
that dimension, I am encoding the
Mm-hmm.
magnitude of all the numbers. And if i'm
Yeah.
if my model wants to perform anything related to the number task,
Mm-hmm.
it can basically manipulate that particular dimensional quantity in my vector, or like, so rotate my vector
Mm-hmm.
around that particular dimension.
Yeah.
So
Yeah.
I am
Mm-hmm.
doing operations which are relative to the particular dimension. So if I fix one dimension to be a numerical dimension, I can basically
Mm-hmm.
try different things over that. So that's
Yeah.
the idea.
Yeah. Yeah. Got it. Thank you. Go ahead, please.
Okay. So I mean
You
that's
tell
the
me one
base.
thing.
Yeah.
In their paper in XVAL, how did they enforce this orthogonality condition while
Oh, they don't
training anything?
they don't enforce orthogonality condition, but they have observed that model because even in an n-dimensional space, model usually learns to basically encode values which are, so model also won't want two vector dimensions to be very close to each other, because then you are not encoding informations which are like very different from each other.
Yeah, so
If I
for in this
if I
case, the base vector, yeah, we can assume that base vector is just like positional encoding of like in
I mean,
rope,
it
like you
can
do.
encode
Yeah.
anything. For
Mm-hmm.
example, if the number is in scientific format or a float number or decimal number, because one question might be from a model that, okay, what was the format of the number? It has nothing to do with the number itself,
Mm-hmm.
right? It
Mhm.
has to do with the information of the
What do
context
you
of
mean by
number.
format?
So, like, if it's a scientific format, or if it's like a fraction, if it is represented as x by y, something. So, for example, you can, if
Mm-hmm.
I am say 0.11, it's a decimal or a float number. I
Mm-hmm.
can write that as 11 by 10 as well. I can write as a scientific notation as well, the e to the power, right?
Hmm.
So, again, so in that case, so it can encode. So the base vector is just an assumption that, okay, there
Mm-hmm.
can be other things, there might not be. Model will like, if it is working, if I fine tune my model for a pure arithmetic task, it might not encode anything on that base vector direction, right? It would only encode anything on my learned numeric directions. But because we don't know what is happening, we just like all the remaining things are combined in a base vector which they are saying there.
Okay, so
Now it
so
can encode anything.
in their paper, they were talking about just the encoding part, or did they train something and showed
Yeah,
that this is working?
they train something on that as well, and they decoded that as well. So then the first question which anyone can ask is, how would you learn this particular dimension? So what they are doing is, let me go to the implementation part. I'll come to the effect of layer norm later on. So this is the implementation. So you have this particular, encoding, or sorry, text string, right, with numbers and text mixed with it. So instead of tokenizing it as a single like a token string, what they do is every number is replaced with a num, and this num correspond to a particular embedding which is initialized like randomly as
Mhm.
all the other word embeddings, but this later on would correspond to the dimension u. So for each number, it learns, first of all, it has to learn a dimension on which it has to encode, right? And this is same for all the numbers. And then you encode magnitude here of all the numbers, and then you basically in your final embedding, so the embedding for your text tokens would be the same as their actual embedding, which they later like which you can initialize randomly, and over the course of time model will basically fine tune it or learn basically them. This is the fixed part. Model will learn this thing, and this is the dimension on which you are projecting your magnitude. So now in your vocabulary, you have a single space to represent any number. And model's task is to basically learn the best possible dimension to encode numbers, or to basically, to basically come up with a good U. And this kind of answers your first question, that how they are trying to impose orthogonality. They don't. It's up to the model that when you do these tasks or when you train them on arithmetic task, it has to figure out that I have to choose a dimension, or this particular embedding has to be in a way that when I multiply this it with the magnitude, the information I encode here would basically, when I combine this proportional embedding and everything else, the rest of the information remains orthogonal with the magnitude which I'm embedding in itself. So this is there like a way of telling model to do it. It's on model to basically figure it out. And transformers are like pretty good in figuring it out later. So like it works. And the second is like how you mask it. So first of all, these would not be just the plain thing. These would be one. So basically, when you do a element-wise product of it, you will end up with the same embedding for all the text tokens, and the number tokens are scaled by the magnitude of those tokens, right? Then when you are training it, so again, the model they have trained is using the language modeling. Right. So when they were masking, you basically whenever you mask a number token, you mask its magnitude as well. So both of these things are masked together, and then they kind of then they did a masked language modeling over this thing, and um, learn the U dimension, or the the numerical embedding dimension, or embedding for that, like base embedding for this particular thing where you scale it later on. As for the decoding is concerned, the first thing is your normal token head. So again, because normal token head is predicting tokens, it would predict text tokens and a num token for any number it has to predict, right? And then whenever there is a num token predicted, there is a separate number head, which is trained based on the MSE loss, your mean square error loss, because this is continuous regression, right? And this head then maps this. So as I said, based on the projection assumption earlier, if most of the information or the rest of the information is in uh, kind of approximately orthogonal dimensions, you can basically project the number onto the numerical dimension and extract this value, and then it is the predicted value. So that's how the entire thing is modeled. So basically, the idea is to not map each, like pre-map each token or each number with a space in the vocabulary, but to map a access for number line, and then encode numbers on that particular number line. So like you basically, this access would become a number line in the model's embedding space, right? And you just kind of subsequently project the magnitude of that number on that number line, and you get the embedding. So in that way, you are using single token for each number, but still you are not giving vocabulary space for each token. And this is very natural because we don't have to have like a separate number embedding vectors for 1, 2, 3, 4, 5, and infinite numbers because they kind of lies on a single dimension. So you can just have embedding for that particular dimension or that particular direction, and then just scale that direction based on the magnitude. So this is their end-to-end. What they're trying to do is to basically enforce the end-to-end continuity for the numbers. Now, one biggest problem and limitation of this model is this idea seems to be very interesting on surface, and you might think that okay, you can encode any number. Like I can encode 10,000, 20,000, say 50,000 using this kind of embedding. Unfortunately, the language model does not work like that. And the first problem they have encountered, which is the major limitation of their work, is that your actual embedding. So I would say again, so for this particular calculation, one note, I would combine the base vector plus u times x in the whole notation of u times x itself. So say my learned embeddings are u multiplied by x for a number, right? Then my actual embedding, which I basically will give to my model here, would also involve positional embedding. Right. So this would become, so my H embeddings which goes into model layers is basically this thing. Right. Now, transformer based models apply layer normalization. Right. So what would be the layer normalization of this? Now, this is a vector. So basically the layer normalization form of this vector would be its norm. Right. So this would be the layer normalization. Now, my question here is, now this is the embedding which model sees. Model does not see u times x. Model sees this, right? In your embedding dimension, which is your u. Now, what if I project this on u? What would it represent, right? So to calculate that, I would first of all make some assumptions here. First of all, the assumption I'm making is that, as I said, the base vector has to be like orthogonal. So again, the base vector here is positional encoding because they also encode another thing which is not numbers magnitude, right? So and as I said, I have like kind of conveniently assumed that there is no other information encoded here. So just the information, the extra information which is encoded is the positional embedding itself. And assuming the ideal orthogonal dimensions, I would assume that the uh, uh, cosine or like the dot product between them is basically zero, right? And I also assume them to be like a unit vector. So their magnitude is one. This is to because if they are not orthogonal, I to basically recover them back, I have to also do some kind of angle vector calculation, which I don't want to. So like these are the simplest assumption. Again, these are not the real scenario which is happening in the model, but it gives you a good approximation of what is happening inside the model. That's why to make our life and calculation simpler, we just use this kind of embedding or like this kind of assumption here. Now, so U is basically my embedding for the num thing. And this is my numbers, magnitude actually, and the P is positional encoding. Now, to basically calculate this, assuming that my X and P are orthogonal, they will make a right triangle, right? So if this is my X and this is my P, right? This, and because this is XU, right? And this is the P. Then this side I can calculate using Pythagorean theorem, right? Pythagoras theorem. And what that would be is that basically you would do uh, so if this is my H, and also this H here is basically my because they are vector addition, right? So if I apply Pythagoras theorem on this thing, I can map it to basically this property. And now, as we can see, this is xu plus p square. Now, this is a scalar, right? So it can come out of the norm or magnitude there. And because of this second assumption, we can plug in the values of this thing and take under root of that. I would get the value for this particular thing, right? So I can basically say my H embedding after the uh, projecting them onto the sorry after integrating them with the positional embedding and applying layer norm will become something like this, right? Now, the question which I asked is now if I project this onto the dimension u, what it shows me. So basically, now if I want to project this, I can just take the dot product between these two because u is by assumption is a unit vector and this itself is a normalized vector. So it's a unit vector in itself, right? So this is basically the projection. And if I calculate, if I plug the values here, it would basically become, oh yeah, it's not, it's vector actually. So yeah, so it would become something like this and just replace the denominator by this thing, right? And then because this is one, because they are the same vector, so this would be, and this is again, these are orthogonal, so that is zero in the ideal condition. If not, then there will be some quantity here as well. And this would this. So actually my projection is not x. My projection is basically x by under root x square plus 1, which is this function. And as you can see, it is linear only for a certain range and not after that. So due to this layer normalization, as the magnitude increases, the way you will encode them. So for example, if my 10 is say 0.95, then my 1000 would basically become 0.995. So the separation between these starts to like vanish away because of this function and how it is actually projected on the numbers dimension as not x but x by x square plus 1 due to the layer normalization. And that's why they had to choose a range of normalization which they have chosen from -5 to 5 somewhere. And so you basically, if you're training it for a particular task, you basically normalize numbers in this domain. So 10,000 by would become, so if this is my max, this would become 5, then this would become something in between these values, and then you will encode that on the number line, which is a big limitation because it forces you to basically know what your max number would be and then train model accordingly. So you're fixing the range over which you will basically also the domain over which you will operate. So if I fix my max number to be say 10,000, it's like 5-digit number. So now if I try to do 6-digit addition, they might map to something which is not ideal or which does not follow this kind of structure. So that's a very big limitation because you assume a linearity, but because of the internal calculation and internal processing, it is not linear anymore. So this was one of the limitation. The second is of use of MSE, which is when you use mean squared error. Now it is good for continuous regression, So, for example, in their paper, I haven't shown the results here because I mean, every paper just shows that their model works like 100%. So they have tested it on the planetary position predicting and the temperature prediction, temperature for forecasting. And because the values there are continuous, their model seems to work better than any other model. But this is a downside for something like in which year, say for example, Cricket World Cup was held, right? It's 2020. If I'm saying 2024, now this model in theory can predict 2023.777998, something like that. Now, MSC with that particular value is like very less because it's very close to 2024. But in the context of this thing, that answer is a waste. So you should actually penalize model like very heavily for that answer. But under this continuity assumption, that would not be the case. So yeah, it enable model to do continuous regression. So for example, if it's analyzing, say, a time series or something like that, where continuity is basically is the main center point of your analysis, it's a good model. If discrete predictions are kind of center point of your analysis, this is not an ideal way to encode numbers, but it is a structured way to encode number, and it gives a lot of information about how you can encode numbers. So, any question about this paper? I haven't put the results. If you want, I can like share the paper with you guys.
Yeah. So, did they try using a post-norm architecture instead of a pre-norm? Because I think
No,
this
no, no.
thing
So what
only.
the idea is to basically develop. So they were trying to not just them, every other researchers who are like doing research over this. What they're trying to do is to basically develop a number strategy which fits in the existing architecture of language
Yeah,
models.
but the problem with their one that you showed right now is with the
Yeah,
normalization,
it's
right? So
yeah.
if let's say in the first layer itself you're just remove the pre-norm to a post-norm, convert that to a
Yeah,
post-norm,
I
maybe
mean,
then.
that is still an open area of research. I mean, we can definitely try to do that in our work. It's just that basically because everybody wants kind of a plug-in approach to increase or enhance the capability of existing language models because
Yeah,
you don't want to compromise on the linguistic capabilities which language model already have,
yeah.
right? Because numbers in itself, they say one thing is I don't want a model which do addition on its own because I can do it on calculator. I always have to I want to increase numbers understanding or like number understanding ability of model because I know that with the text data there is a lot of numbers going on,
So
right?
did they train actually the whole a whole language model, or did they just
So
train
they
something else?
trained a GPT small architecture with a data set which is, if I'm not like, it's table wiki something like that. It's a data which is math focused text data. And
Okay.
that's why a lot of, so when I was seeing their, they have submitted it in the Neuros workshop, and they got it published as well. But a lot of reviews were around that. Okay, how would it fare when you basically, train a language model, the actual language model over an actual large language corpus with this kind of strategy for numbers?
Yeah.
And the answer is nobody knows because as like sole researchers working in research lab, we don't have that kind of resource. And I am very
Mhm.
sure no company would basically go ahead and implement this and publish it. Okay, it worked or not. If it worked, they will just, adapt it and don't never reveal that. If
Yeah.
not, it's not, right? So I mean, that's why later paper, I haven't included that paper here in this presentation because of the time, but there is the recent paper in triple AI. What they are doing is they have so when they have pre-trained number embedding separately, and
Mhm.
then using approaches from like, so vision language model, you use projection, right, to project the learned embedding into the model space, right? So they are
Mhm.
also using some kind of modified approach of clips like that to basically then align the already learned number embedding of the large language models with their embedding. In that way, you can basically plug those embedding into models like Llama and like Quen, which is open source, fine tune them, at least the small models, and then see how it works. And then they have calculated perplexity to see how it basically compromised with the linguistic capabilities. And
Mm-hmm.
it turns out not a lot. They just compromise a bit, but on other tasks, the accuracy enhancement is quite good. So if your work is kind of number focused, you might want to fine tune your model using these kind of strategies. But the main research gap is that other than that, I haven't found that that's the newest paper. It's 2026 AAAI journal paper. There are not a lot of papers which basically try to adapt this into existing pipelines. So
Mm-hmm.
either you will be training a model from scratch, which you don't know what happened with the language capability. And if not, then your approach is not like very well validated at all.
Mm-hmm.
But this gives a sense that, okay, there is a need of like a structured reasoning, a structured like a embedding approach for numbers, which if you do that, it enhances at least the numerical capability. On what cost is yet to be figured out, and how you can basically balance this thing together. This is second one, so I think I have like in half an hour time as well. So this is the phone precise single token number embedding where Fourier features. So the idea of this is that it maps the number into embedding space with their Fourier features, and it also encode each number as a single token. But the embeddings are not just like a single vector. It uses two dimension of your embedding space per digit. How? I'll explain it in the derivation later. This is inspired by the research on interpretability in language models. So a recent research in like last year's Neuros paper, not last year, 2024's Neuros paper actually has shown that if you use a good enough language model. So I'm not talking about GPT-2 is small because that's a very small architecture, but a newer, bigger architecture with sufficient number of parameters like Llama. So they have tested their approach on Llama 3, if I'm not wrong, Llama 3.7b. So then what they have observed is that without any other without enforcing any structure or number embedding, the number embedding which model learned or the embedding which model learned for these numbers was basically sparse in Fourier space. So as here we can see, there is spike at t equals to 10, t equals to 100, t equals to 5, t equals to 2. So it tries to basically organize the embeddings in some kind of frequency based structure, which preserves the periodicity and some kind of order as well. So though it's like an inefficient way of doing it, because model then have to like map each and every number token to this kind of space, which starts as a random vector. So it takes a lot of time for model to basically arrange the embeddings in this way, but it tries to do so. And inspired from that, what they did was to encode each, so to start with a digit which is encoded as sine and cosine. Okay. So what I mean is that their embedding of a number x would look something like this. So it's a vector with components like cos 2 pi by t1x, sine 2 pi by t1x, cos 2 pi by t2x, and so on and so forth till tk, right? And every two value here basically encodes a point on a circular embedding or on a unit circle, right? So phone represent each digit using only two dimensions. So it's like per digit you are using two dimension for encoding a digit. Why digit? Because this T1, T2, I'll explain, I'll derive it later, but for now, these basically equals to 10i. So it basically kind of, so if I shift it from here to here, it does not changes my operation. But if this is the TI is 10 and my number was say 1, 2, 3, 4, what it will return me is 4, which is x mod 10, right? Here. So that is why I'm saying, and the next would be 100, the next would be 1000, the next would be 10,000, right? So it encodes each digit of number using uh, two dimension in the embedding space. Now let's talk about first of all, I'll introduce the concept of circular embedding. I'm pretty sure you all are familiar with that, but anyway, just to like formalize it a bit. So say this is my circle. Uh, so on this circle, if this is my x and this is my y, okay. So any point on this circle can basically be represented using this angle theta, right? So if I assume this to be a unit circle, this radius would be 1, right? So this is x, this is y. The projection of this on x is basically my x coordinate, and the projection of this on y is my y coordinate. And based on the trigonometric identity, this projection is basically my cos theta, and this projection is basically my sine theta. So I can represent this point on a unit circle in a 2D plane using just this angle theta, right? So this is the central idea of circular embedding of a digit. Now, what will happen is, say, for example, and the 2 pi here, so this is very similar to this thing. This is my argument, which I am kind of mapping. And 2 pi here means that after one rotation of 2 pi, I would basically end up here, right? So to basically test that out, I'll give you example of that. Say I want to represent, and this say assume T1 equals to 10, right? And I want to represent numbers 8 and 18 using this circle embedding. Just this circle embedding with one time period, like with one T here for me, right? So 8 would become basically, uh, wait a second. Yeah. So 8 would become basically this and 18 would become this, right? And if I plot this on the circle, and let me just calculate the actual value of sine so I can basically point that out. Okay. So like for example, cos 2 pi, which is 360 multiplied by 0.8 is somewhere here. And if I multiply it with 1.8, so the value is 0.309. And for 0.8, 1.8, if I do it for even like say 2.8, it would again and again come back to this point. And the reason for that is that you're, so if I, instead of doing x by t1, if I write it as 2 pi by t, which is 2 pi by 10 here, my period of these two, 8 and 18, is basically 2 pi by 10. So after each 2 pi by 10, it will end up at the same point of the circle. Like it will complete a full rotation around the circle. And hence 8, 18, 28, all of them would have this as like their cause. And again, sine, I can also calculate like that. Sine is, so it would be somewhere here then, because it's 0.39 and minus 0.95, right? But the idea is that this, after this time period, number repeats. And because this is 2 pi by 10, basically 2 pi is the full rotation. And if you divide that by 10, after every 10 number you completed on this circle, you basically end up. So if this is 0, 10 is here, right? You will end up here again and again and again, because if this is 0 and this is 10, it's again 2 pi. So it's a full rotation. So again and again, and if it's 1, then 11 is a full rotation, right? So this is basically how you can represent the values on a circle which repeats after a period, right? So that's the basic thing which they have done. Now, this is the one, so this is for like one pair of your t, which is like 10, right? You can do 100 and it would repeat after 100 interval. So all numbers from 0 to 99 would be on this circle, and then 100 would again come back to this particular point, right? So now,
What is the motivation behind using circular embeddings? If you are going for periodicity, like why do you need periodicity in number embeddings?
because as I said, the interpretability work was shown that model basically tries to encode them as Fourier feature or periodic numbers. And it is good for periodicity because you can basically then kind of you're like kind of, decompose every number into its equivalence class. And I'll show what it helps in. It's like it's a carry implicit operation. So because model can learn geometry. So if you assume, if you want model to learn say plus, it can't do that. But what it can do is, if I have two numbers embedded as say cos A sine A and cos B sine B, I can calculate cos A plus B and sine A plus B, because they are just rotation of those vectors in the embedding space. Because the internal operation which model perform is the multiplication with learned W's, right? And what those learned W's can do is basically rotate. So in attention layer, you can rotate the vector, you can translate the vector, just like a normal neural network can do that, right? In your MLP layer, you can add non-linearity to those. So if you learn the geometric manipulation, you get two vectors of any arbitrary number. You can rotate them, you can multiply, you can rotate them, translate them, apply some nonlinearity over them, and get a vector, and then project it back to the number space, and that's your answer.
Mhm.
But if you try to learn a particular algorithm, okay, this if this is the number, that's my weight to multiply it with this, so I can add this to that, you can never learn those weights because it won't generalize at all. So that's why I named this thing from token to geometry, because model for a language model or for any NN model to basically do number operations, we can't expect them to do it like human do, right? We have to represent these concepts as geometrical manipulation in that vector space. Because the way model do things is basically by translating, rotating, manipulating, or applying nonlinearity over these learned vectors. So
Okay,
that's
but
its.
then one of the questions that I have is like how does a model then differentiate between the embedding of 0.8 and 1.8 if you both of them give you the same
Yeah,
kind
so
of an embedding?
it won't, and that's the reason why they are using 10. So like I'll formally introduce. So that was the circular embedding. Circular embedding, as I said, I'm like trying to describe how a particular pair of point would end up on a circle. Now, the actual phone or the Fourier feature embedding is basically let m be the integer length of a number. What I mean by integer length is the integer part of it. right? And let say n be the fraction length, right? So if I have number like 4.17, the m would be 1 and n would be 2 here. So for all, so my phone would basically take these three arguments. It would take the number, it would take the integer and this would be, so my, so if I say my circular embedding phi is basically, if I say phi x somewhere, phi x t, it actually means a vector of 2 points cos x, cos 2 pi by tx and sine 2 pi by tx, right? So this is a shorthand which I'll use later on in this. So now this phi x, so I would use phi x, uh, then my t would be minus n plus 1. Phi x t minus n plus 2 till the point phi t phi x t m. So this is my entire Fourier embedding. So here, if I take this, this would be minus 2 plus 1, which is, and again, ti is basically 10i, right? So here it would become my phi 4.17 and t would become, it's t to the power, so it's 10 to the power minus 1 or minus 2 rather. No, minus 1. Yeah. Then this would become phi 0, right? Which is 1. So it's, in other word, is 0.1. This is 1. And this is 10, right? And the way it encode the number would be, this would be encoded on a circle which after every 0.1 come backs to the origin. So you can basically, the distance between, you can basically kind of very precisely differentiate between these digits, right? Because after every 0.1 you are here. So it encodes value in this range, right? After 1, if you are here, it can basically embed. So you have this 2 pi circumference to encode values from 1 to like every 1 to 2, 0 to 1, right? So you can very precisely embed the values for like 1, 1.1, 1.2, something like that, right? On 10, it's a bit coarser because now you have this much space to represent values from 0 to 10. And the problem, so one can say, because 10 actually kind of take care of all these previous modulos, right? I can directly represent 4.17 because it will have a embedding on this space because after every 10 I am repeating, right? But the problem is as it increases, so for example, if I take two value x and x plus 1 here, now what is the angular difference between the embedding of these two things? It's 2 pi by t for this, 2 pi tx is the embedding of this, and 2 pi, that the theta which it will make would be this, right? And the theta which would x plus 1 will make is this. If I subtract them, the difference of the theta which I'll get is this. As t approaches a very large number, you cannot separate a consecutive number very precisely. And this is something which also your normal sinusoidal positional encoding do as well. You do like sine cos for the indexes, right? In the in the positional embedding. And the idea is that the upper values of that column vector where the index is small for your 10 basically captures the local positional context very precisely, and the later values capture the global context and they cannot basically capture the local context at like very precisely. So that is what they are trying to achieve, that you have digit level separations. So each of the digit can be because the fractions have to be very precise. They vary between points or something, right? So their circle gives them more area to encode these precise numbers or precise differences. Whereas larger numbers, they 4.17 will also have encoding on this, right? But the difference between 4.17 here and 0.17, the information about 0.17 which I can get from here is more, more informative than this what I can get from this representation. So that's the whole idea, that not to use one single T. You can. It's a very valid question. I had that question first, like when I read it this paper. Why not use like a one single T? But this gives you a more digit-wise precision. And also, if you're using a large T, how would you fix that? Here it's like M and N dependent. So you can basically decompose any number into like a family of cause and sign features for any given length, right? Till the point, because this will basically live in a space which is like twice M plus N. So the time it is less than your n your D model dimension, you are good. So if your D model dimension is 768, you can represent any number which is which is half of that, right? Of the number of digits. So that's the basic like a Fourier feature idea. And that is like how they do this. Now, why this is helpful is something which I can explain. Okay, one question. Do anyone wants to like leave? Like, is this going like long for anyone? So I can just quickly go over the main concepts and then we can do later when we can discuss things after that.
Yeah, I think that would be better because it's already 1.5 hours. So
Yeah. Yeah, okay. So basically, the idea is to represent them as like Fourier embeddings, and quickly I'll just say like why. So for example, if I have number like a very simple number like this, and I want to like add number to it, say 1111, right? When I will basically add cos and sine of this, I would get 5, right? This would be my first digit. But for the second two features, here, these two features would basically give me this. So if I add cos A plus B here, it is 34 plus 11, right? Which will actually, because they are representations, right? So they will actually give me this 5 as well as 4. Now, say if this were to be 6 instead of that, this would be 0, this would be 1. So I have to keep track of carry. But in this, when I do this over this, it would actually give me the actual answer for this, which is right. So I don't have to take care of carry. Carry is implicit. At each with each pair of sine and cosine with the digit based granularity, I just have to predict the answer for that, and the next digit granularity would automatically take care of my carry. I don't have to worry about that in the model. Right. This is like a bit of a abstract concept, so I think we can, if you want to discuss it, we can take it after the presentation. Okay, so I'll quickly go over. I was thinking about deriving the properties, but I think I can just quickly go over them. So the thing is, if you have 2 point cos theta sine theta on a circle, tan theta would be sine theta by cos theta, right? So you can do tan inverse theta and you can recover the theta or the angle. The only thing is, it would only give you theta in minus pi by 2 to pi by 2. Because its domain is that only. So they used to recover theta using something known as two argument inverse tangent, which is basically tan inverse theta, which just take cares of the sign of what your the signs of cos and sine values. So if sine if your y is negative and x is positive, it can just add a pi to it to basically transfer that to third quadrant instead of the first quadrant. Otherwise, pi by 4 and 5 pi by 4 for tangent have the same value, right? So to basically recover it in the domain of not just pi by but 2 pi, they use sine. So that is known as arctan 2. So basically by using that, the lemma is that given any pair of cos 2 pi by tx and sine 2 pi by tx, you can basically recover the angle theta. right? And this theta is a unique angle mod 2 pi. Why I'm saying mod 2 pi, in the 2 pi domain, it's a unique angle because we are doing arc 2 tan. So now it's not just in pi, it's in 2 pi domain. But after a rotation of 2 pi, for two values which are separated by this period, the angle would be same. So basically, what you will recover from this is theta mod 2 pi, not just a unique theta for any value. So that's the first assumption or first lemma for them. Now, because we are using 10 to the power I can basically recover digit-wise, digit-based granularity for each digit, because my 10 to the power 1 would basically give me a unique theta mod 2 pi by 10, right? So after 10 values, you will end up there. My 2 pi by 100 would give me theta mod 100, right? So if I kind of combine them, I can basically get a unique number out of it, right? Because every angle would be a digit representation of where it is, and where it is in number and where it is in the circular embedding, right? So this would helps to basically, uniquely encode the numbers. Again, their process of like encoding them with the model is pretty same. You just replace everything with a num token, and then you will predict a Fourier number embedding, because this is a deterministic number embedding which you can just prepare by applying sine and cos on that number. You can just basically predict embedding for that particular num token on the fly and just put that through the model. Decoding is a bit different from the model, so I'll just quickly go over the architecture here. So encoding is pretty simple. You have the embedding for the num, you have the pause embedding, which is a positional embedding, and you have the Fourier number embedding for that particular number. Give it to model. Now, while decoding, the first two values of hidden state would basically be two dimension, and you would basically predict first digit using them, second digit using next two. So the prediction is digit wise here. And it is trained using cross entropy loss because again, it's a discrete prediction. Now it's classification, right? So each of these tasks is a classification of number in range 0 to 9, right? And that's how it builds on that. And as I have explained in the earlier example, now the first two component would give me say 6, 4 plus 6, right? 4 plus, oh, sorry, 0, 4 plus 6, जो 10 hota hai, which is 10, right? So it will give me a 0 there. But the next two, because their granularity is 100, I don't have to worry about a carry of 1. It would basically add up and give me that 10th digit straight away here, and it keeps happening. So that's why they kind of do a continuous based in encoding and a discrete decoding here. And it's good for the task which I mentioned in the XWell paper, because like now if you predict 2023.7766, it would basically like you there is no way of predicting that because your digits are fixed, right? So you would only have those many embeddings to predict 4 digits. Right. So you map it on the circle, and based on whatever the closest integer to that particular point, that's the classification. So you just take the argmax of that entire thing, right? And that is your prediction. So that is in a nutshell of how Fourier number embedding work. I haven't included results for this as well because like they have shown that their model is working with 99.997% accuracy over 10,000 arithmetic example, which I mean definitely they also curated them for their work. So yeah, it's pretty obvious that it will work on that. There are other papers, as I was saying, there is a paper GeoNum, which I haven't like included in this presentation, which kind of then, because these papers need a full retraining of the model. Then they are taking ideas, inspiration from the image to text alignment, vision to language alignment, and then you can basically train a modular embedding separately, and then project that in language model and see how that works, because that is a more feasible methodology to basically enhance the numerical understanding and capabilities of language model. Because to be honest, no one need them to basically do calculations. You can also use calculator. You can plug a calculator tool. What we actually need them to have some representational understanding of numbers. So when they're analyzing documents, or when they're working in a STEM task, what they're predicting, what the confidence is, that should be deterministic, or that should at least be interpretable and not some random thing. So that's the basic need of why we should work, like why we are working on this thing. So with that note, thank you guys. Sorry, I was not able to derive all the equations. If anybody wants to um, have another hour-long mathematical calculation, boring stuff, you are most welcome to reach out. Okay.